Welcome guys, welcome back to another session on Laplace transformation. So on the last video we treated the Laplace of cos at, which is a hyperbolic function, and we got a function of x which is s divided by s squared minus a squared. So this is what we did on our last video, and I advise, if you have not seen the last video, I advise you go and watch the last video, then we come back to this one. So today we are going to be looking at another section also on Laplace transformation, which I believe is the last derivation of mostly our standard solution to Laplace question. So I believe this is our last derivation of our standard solution to Laplace transformation. Then we are going to be looking at theorems and other aspects on Laplace transformation. So today I believe we are going to be looking at how to get the Laplace of an arithmetic function. For example, we have been treating trigonometric functions like sine, cosine. Then we treated hyperbolic functions like cos and sine. Now we want to treat the Laplace of a hyperbolic function. Hyperbolic function can be of any order. It can be a quadratic hyperbolic function. It can be a quadratic function or a polynomial or a linear function. But it depends on the power of the degree of the function, right, or the highest degree of the function. So basically, the Laplace of a function of nth order or nth power, we are going to be treating it today. So today we are going to be treating how to calculate the Laplace of t raised to the power n, right? Remember, all we have been treating are functions of t, right? So this is an arithmetic function of t of the order n of t raised to the power n. N is a constant. It can be any value or any figure, right? So now we don't know this. We're looking for the Laplace of t raised to the power n. So I believe this is our last derivation of the standard solution to Laplace expression. Then we're going to be treating questions and questions. Then you see that where this derivation comes in is very handy. So now before we proceed, to remind you of the derivation of, remind you of the expression of the Laplace of a general expression of the Laplace of any function of t, which says Laplace of function of t is equal to the integral coming from 0 to infinity, right, of the function of t times minus st dt. Now you see that we make use of this derivation in almost all the derivation in past videos we were making, and we said that the derivation of this, or the Laplace of any function of t, will surely give you a function of s, right? Which I said this in our last video, and so I advise, if you have not watched the last video, I advise you to go and watch it. So I said this, that all the answers we have been getting are always in function of s, right? So now today let's see how to calculate the Laplace of t raised to the power n. So now let's proceed. So putting this in this, we'll be having the Laplace of t raised to the power n, which is equal to the integral coming from 0 to infinity, the function of t, which is t raised to the power n, times exponential minus st dt. Right? So I believe we are going to be applying or integrating. This is called the definite integral coming from 0 to infinity, right? So I believe we are going to be looking at, before we apply the limits, we need to integrate it first, right? So integrating this, will be having integral t raised to the power n exponential minus st dt. Now we're having two functions of t, right? Because we are integrating with respect to t, so we are having two functions of t. We are having t raised to the power n, and we are having exponential minus st. So when we have two functions of t, when we are integrating two functions of the independent variable, we will be applying what we call integration by parts. So the independent variable we have here is t, right? So we are integrating two functions of the independent variable we have. So we will be applying what we know as the method we know as integration by parts. So integration by parts method says what? Integral u dv is equal to uv minus integral v du. So I said the formula for the integration by part formula says the integral u dv is equal to uv minus v du, right? So now what are we going to need? Because this is the integral, this is equal to this, right? So this is the integral we are trying to get, right? So what are we going to take as u, and what are we going to take as dv? Now, following the sequential order for integration by parts, the arithmetic comes before the exponential, right? So now the arithmetic we have here is t raised to the power n. So we take u to be t raised to the power n. Now we take dv to be what? Exponential minus st. So we are going to be differentiating u and integrating dv, right? So differentiating u will be having du dt, which is equal to, so differentiating t raised to the power n is going to be n times t raised to the power n minus 1, right? Now integrating the v, we'll be having integral dv is equal to integrating exponential minus st, you're going to be having exponential minus st divided by minus s, right? So integrating the v will be having v, right? So v is equals to this, right? So now we're going to be substituting this into the expression or into the formula or the expression we have. So substituting this into the formula or expression we have, my u is equal to what? My u, which is t raised to the power n, right? My u is t raised to the power n. So putting this, we're having integral t raised to the power n exponential minus st dt is equal to u, which is t raised to the power n, times v, which is exponential minus st divided by minus s, right? We're having exponential minus st divided by minus s minus integral my v, which is the same thing, right? Exponential minus st divided by minus s times my du. Now this is du dt we have here, right? So if I make du subject to formula here, what am I going to have? So taking dt to the back of this. So taking dt to the back of this, so I'm left with du is equal to nt raised to the power n minus 1 times dt. So my du here is equal to nt raised to the power n minus 1 dt. Right? So now let's multiply 2 by minus and minus cancel minus, right? So we are left with t raised to the power n times exponential minus st divided by minus s plus. Now n and s is an irrelevant variable, right? It's a variable, it's irrelevant. So but n here is a constant, so we can take these two out because s is irrelevant because we're not integrating with respect to s, we're integrating with respect to t. So taking n and s at the back of the integral sign, we'll be having n divided by s integral exponential minus st times t raised to the power n minus 1 dt. This is integral t raised to the power n exponential minus st dt. So now we're going to be assuming the following. Now assume that I subscript n is equal to integral t raised to the power n times exponential minus st dt. And now if you look at this place, we're having something similar to this, but the difference is that this is n and this is n minus 1, right? We're having something similar to this is integral exponential minus st times t raised to the power minus n times t raised to the power n minus 1 dt. We're having here also integral exponential minus st times t raised to the power n dt. So they are similar, but what's the difference is that their powers are different. The power of the arithmetic is different. So here is n and here is n minus 1. So we can assume also that the I, now since this is n minus 1, so we can say I subscript n minus 1, and let's assume it's equal to this exponential, let's say t raised to the power n minus 1 exponential minus st dt. See that we didn't follow through the normal process of integration by parts because I believe we are going to be having some repetition, but we are not going to be having the same thing that we can substitute I for. But this is a very understandable process, so I want you to follow me step by step. So continuing from where we stopped, right? So I assume let I subscript n be equal to this, and let I subscript n minus 1 be equal to this. So substituting and replacing this with this for the two i's, you'll be having I subscript n is equal to t raised to the power n times exponential minus st divided by minus s, right? I replaced this with I raised subscript n, right? And replace I subscript n minus 1 with this, right? So plus n s subscript n minus 1, right? So now what we're having here now, so now let's proceed. So what do I do here now? So having I subscript n, and this is t raised to the power n exponential minus st divided by minus s plus n divided by s subscript n minus 1. So having I subscript n is equal to this, right? So now see that we've gotten we have not actually gotten the exact value of I, but we have successfully expressed I to be equal to something, right? So now we can apply our limits. So since the actual question says integral from 0 to infinity of this, right, of t raised to the power n exponential minus st dt, right? So we are going to be, and since I here is equal to the integral of this, right? So applying our limits, we'll be having the full value of I, right? So we'll be having the Laplace of t raised to the power n, right? So now let's proceed. So applying my limits, right? Taking our limit from 0 to infinity. Now, but in this case, if you can remember, we said let I subscript n minus 1 to be equal to the integral, right? Coming from 0 to infinity of t raised to the power n minus 1 exponential minus s t, right? Now in this case, there's still an integral sign here, right? So we are not going to be taking our limit towards this I subscript n minus 1. It's towards this side, right? Because in this case now it's still in representation of the integral sign, right? It's still in representation of this integral sign. So taking our limit, this place becomes this place. When we take our limit now, this place now will take this integral sign, right? Why only this place will take our limit? Because this place now there's no integral sign here. Because why we are not taking our limit towards this side? Because there's still an integral sign here that will carry this limit. So remember, this thing is equal to this, right? If I put my limit, so putting my limit, this my integral sign will have this, right? So in this case now, our limit will not be concerning this one. So you have to split it. So we'll be having t raised to power n exponential minus st divided by minus s, taking our limit towards this place from 0 to infinity, plus then we have this n divided by s I n minus 1, right? So now we're going to take our limit only towards this side, right? So taking our limit towards this place, we'll be having, so if in this case now, if I put infinity and put my 0, what am I going to have? So taking my limit towards this place, limit t to infinity of t raised to power n exponential minus st divided by minus s minus limit t to 0, right, of t raised to power minus n, t raised to power n exponential minus st divided by minus s, right, plus this n divided by s n minus 1, right? So limiting t to infinity here. Now if I put my infinity here, everything here becomes 0, right? So we'll be having 0 minus, putting t to be 0 here, exponential 0 here is 1, and putting t to be 0 here, 0 here, 0 raised to power n is also 0, so here also becomes what? 0. So we are left with only n divided by s I n minus 1, which is equal to I subscript n. So now this is what we are left with. So 0 minus 0 is 0. So continue from where we stop, right? 0 minus 0 becomes 0, right? So we'll be having n divided by s I n minus 1 I subscript n. So in this case now, if I choose to replace n with n minus 1, right? Because n can be any figure, n minus 1 can be, so if here is 3, here is what? 2, right? Here is 3. If n is equals to 3, here is equals to 2. So if I choose to replace n by n minus 1, so what do I have? Putting n minus 1 here, we'll be having n minus 1, right? Replacing n here with n minus 1, replacing n here with n minus 1 divided by s, right? Replacing n here with n minus 1, so this is n minus 1 minus 1, right? So this becomes n minus 1 divided by s n minus 2, right? The same process, if I replace here this n here with n minus 1, what will I have? So this is n minus 1 minus 1 becomes n minus 2, right? So this becomes, replacing n minus 1 here, this is n minus 1 minus 1, right, divided by s, right? Replacing n minus 1 here also, this is n minus 1 minus 2. So this becomes n minus 2, n minus 2 divided by s n minus 3. So if you can see, there's a pattern. So we are taking note of this, taking note of this, taking note of this. So you see now, I substitute n minus 1 is equal to n minus 1 divided by s n minus 2. I substitute n minus 2 is equal to n minus 2 divided by s n minus 3. So all this now, we are going to substitute, since I substitute n minus 1 is equal to n minus 1 divided by s n minus 2, we are going to substitute it into this, right? Now after we substitute this, in respect to n minus 2, we are going to also substitute it in. So what we need is just this expression only. So what we need is just this expression of I substitute n. I'm going to repeat myself. I said, replacing n with n minus 1, we had this. Replacing n here, replacing this n here with n minus 1, we had this, right? So we're going to substitute this now in this, right? I'm going to also substitute this in this. So now let's substitute this one now in this. So substituting I substitute n minus 1. Anyway, I see I substitute n minus 1, I'm going to put n minus 1 divided by s substitute n minus 2. So we'll be having I substitute n is equal to n divided by s, right? Now, any I substitute n minus 1, I'll replace it with this, right? Times n minus 1 divided by s n minus 2, right? Now I'm having I subscript n minus 2, and we got here that I subscript n minus 2 is equals to n minus 2 divided by s n minus 3. So I'm going to erase it. So substituting I subscript n minus 2 in this, we'll be having times n minus 2 divided by s n minus 3. So you see that the sequential order we stopped here is n minus 3, right? So if I say let n be equal to 3, right? So I'm going to be having I subscript 3 times 2 times 1, right? Then we're having I subscript 3 minus 3, that's I subscript 0. Am I correct? So since we're having I subscript 3 minus 3, which is 0, so now there's a pattern. So continue from where we stop. Now I said assume we're having I subscript 3 here. So if I put 3 here, so this is 3 minus 1, this is 2, 3 minus 2, which is 1. So I'm having 3, 2, 1. If it's 4, which is 4, 3, 2, then remember we're having I subscript n minus 4 after we have substituted it again in the previous one. So that's how it will go, get into 1, right? So now this is only for 3 consecutive series, right? If we had done for 4, we would have gotten I subscript n minus 4 here. So what we would have gotten for 4, it would be n minus 1, n minus 2, n minus 3, then I subscript n minus 4, right? But in this case now we're substituting at only 3 consecutive series. So in this case now, we're going to be having, if you are substituting it for any figure, if it's 4, if it's 4, it will be, okay, let's do for 4. If it's 4, we'll be having I subscript n, which is equal to n divided by s times n minus 1 divided by s times n minus 2 divided by s times n minus 3 divided by s times n minus 4. So that if I say let I be equal to n, let n be equal to 4. So this will be 4, 3, 2, 1 times I substitute 4 minus 4, which is I substitute 0. You see that there is a pattern. For every n equals to 3, n equals to 2, you eventually get the numbers to be equal to, so going down towards 0. So if you can remember our factorial sign, factorials, all numbers move down towards 0, right? So if I say let n be equal to a certain number, it will move down to 0, then we'll be having I subscript 0 here. So I can rewrite the general term to be, for example, let me write this. So I have n minus 1, n minus 2, n minus 3 divided by, now we are having how many number of s here? 4 numbers of s, right? Which is the same number of n, which is 4, right? If I assume let n be equal to 4 here now, the number of s I'm going to get is equals to 4. But from here, let n be equals to 3, right? Because the number of s here I'm having is equals to 3. So given this pattern, so the number of s is equal to n, right? So if I say this is 4, this is s raised to power 4, this one will be s raised to power 3, which is the number, which is n. So I can say this is s raised to power n, right? So times I subscript n minus 4. So if I say let n be equal to 4, eventually 4 minus 4 will be equal to 0, right? So I can replace this with 0. Now you notice that because we assume that the Laplace of t raised to power n, which we assume to be equal to, going from 0 to infinity, of t raised to power n expression minus s to t, right? Which we also assume to be equal to I subscript n, right? So that means the Laplace of, that means I subscript 0 will be equal to the Laplace of t raised to power 0, right? Now if you can remember when we did the Laplace of a, right? Or sorry, when we did the Laplace, yes, if you can remember when we did the Laplace okay, yeah, so t raised to power 0 here is equal to what? 1, right? So this is the Laplace of 1. If you can remember when we did the Laplace of a, the first video I treated the Laplace of a constant, So the Laplace of 1 here is equal to what? Laplace of a is a over s, right? So the Laplace of 1 is equal to what? 1 over s. So we're having 1 over s. So since the Laplace of t raised to power n is equal to I subscript n, that means Laplace of t raised to power 0 is equal to what? I subscript 0, right? So I subscript 0 is equal to what? 1 over s. So I subscript 0 is equal to 1 over s. So I'm going to substitute it here. Over s, right? So substituting I subscript 0 to this, will be having I subscript n equals to n minus 1, n minus 2, n minus 3 times 1 over s divided by s raised to power n. So we're having additional s. So if it's n equals to 4, the number of s here is going to be what? 6. So it's going to be 5. If it's n equals to 3, number of s here is going to be what? 4. If it's n equals to 6, number of s is going to be 7. So we're having additional number of s. So this can also be written as n minus 1, n minus 2, n minus 3 divided by s raised to power n plus 1. Right? So now if you remember our factorials, factorial of 3 factorial, for example, 3 factorial is equals to 3 times 2 times 1, right? 4 factorial is equals to 4 times 3 times 2 times 1, right? So n factorial now is going to be equal to n times n minus 1, n minus 2, n minus 3, and so on and so forth, right? Until it gets to 1. So that is the same thing that happens here. So I can replace this now with n factorial. So replacing this with n factorial, so we are having I subscript n is equals to n factorial divided by s raised to power n plus 1. So the Laplace of t raised to power n, which is equals to the integral coming from 0 to infinity of exponential minus st times t raised to power n, which is also equal to I subscript n, as we assume it, is equal to n factorial divided by n x plus 1. S raised to power n plus 1. So the Laplace of t raised to power n is equal to n factorial divided by s raised to power n plus 1. So that is the final answer. So we're going to be looking at some examples to see how to get accustomed to how to use the Laplace of t raised to power n, or any n, t raised to power 2, t raised to power 3, and so on and so forth. So I believe we should jot this down. Now let's proceed. So guys, I believe you understand how we got the Laplace of t raised to power n, which is n factorial of x raised to power divided by s to power n plus 1. So we are going to be looking at let's say one example, then I can drop some exercise for you to practice through, then you can comment the answer you got in the comment section below. So now example 1. Find the Laplace of t raised to power 3. Very easy. Since the Laplace of t raised to power n is n factorial divided by s raised to power n plus 1, so the Laplace of t raised to power 3 is going to be 3 factorial divided by s raised to power 3 plus 1, right? Where n is equals to 3. If I compare this, n is equals to 3, right? So having 3 factorial divided by s raised to power 3 plus 1. So this is which is equal to, so 3 factorial is equals to 3 times 1, 2 times 1, right? Divided by 3 plus 1 is 4, divided by s raised to power 4. Right? So the Laplace of t raised to power 3 now is equal to 6 divided by s raised to power 4. So very, very easy. So I'm going to drop a particular exercise for you to practice through. So your own exercise. What is the Laplace of t raised to power 4? So you can practice through this. As well at your leisure time, or after watching the video. So thank you guys for watching. Please and please subscribe.